Audio. Start video. Okay. There we go. That's not too bad. Wonder if I could move it over just a tad there. There we go. Yeah. Hey, we have a student already. Christy's with us. Good deal, Christy. Yeah. Let's see if we got anybody else. Yeah, Christy, it's just you and me right now. But the others will show up pretty soon. We have 6 minutes before class starts. Do you have any questions? Earth calling Christy, Earth calling Christy, come in, Christy. Well, okay. Christy's not going to answer me just yet. And we're waiting for the others to show up, and class starts in about 6 minutes. But we're early. We're going to study electric flux. I typed the wrong letter on my schedule. I called it electric flux. Well, I don't know what electric flux is, but flux is what it is. So if your schedule says flux, get rid of that and put an X in there because it's supposed to say flux. Christy, unmute and say hi. Earth calling Christy, Earth calling Christy, come in, Christy. Well, maybe your microphone doesn't work. We're in chapter 6. And let's see what the title is on that chapter. I'm just curious. Chapter 6, it says here, Gauss's law. We're going to study Gauss's law. Gauss's law. It starts off by explaining electric flux and Gauss's law. Well, okay. Let's see if anybody else showed up. Nope, it's just you and me, Christy. I got your labs all graded, and I'll give them back Thursday night. I was looking at the schedule. This Thursday we do series and parallel circuits. That's the lab. And I think a week from this Thursday is your exam. You're going to have your exam in the lab at 5:30. You can look on the schedule, see if I'm telling you the truth. It says here, exam 1, the 10th of September. Well, that's a week from Thursday, isn't it? Instead of having a lab, we're going to have the test. Okay, well, that's fine. And then the next Thursday night, we'll have another lab. I think the lab that Thursday night's going to be on capacitors. Let me look and see here. Yeah, it's going to be a lab on capacitors. This test coming up a week from Thursday is over chapters 5, 6, and 7. We probably ought to get going because we haven't even done chapter 6 yet, but we're going to tonight. And next Tuesday night we'll do chapter 7. Okay, well, it's darn near time for class. I thought I'd have a short review of stuff we know.
I have an alias.
You know Coulomb's law. That's really the basis for our course. Ta-da, there it is, Coulomb's law. And see, if you make one of these a test charge and divide it, then you have your electric field for a point charge. So the electric field for a point charge is you could put a 1 there if you wanted. See, we divided through by that test charge. And there's the electric field of a point charge. But we're having a little 5-minute review here. And then we learned how to do the electric field for a short charged rod. And it was equal to sometimes they use an R there or some other symbol like a D for distance or an A. Now that angle there, that's kind of tricky. If you have your rod like this, the A is the distance from the rod, and the electric field would go that way if it was positively charged. Now, if it was negatively charged, if you put a bunch of electrons on it, the electric field would go this way. But what is this angle? Well, it's this angle here. Oops, let me see if I can draw that better. There it is. There's that angle theta. Actually, what it is, it's the electric field along the perpendicular bisector of a short charged rod. Let's see if we got any more customers here. Oh, yes. We've got Zach, Phoebe, Jacob, Daniel, and Christy. Good class. So somebody out there say hello so I can find out if I'm getting through to you. Somebody say hi.
Hello?
Yeah, that's it. Now who was that?
Jacob.
Jacob, good going, Jacob. So your microphone's working.
It's a bit spotty, but it's on. Yeah.
And well, my microphone's working. And Jacob, can you read the board there? Okay.
Yes, sir.
Good, excellent. All right. Well, then we Jacob and the rest of you were doing a short review here of stuff we've learned. And then we did a very long charged rod. If you have a very long charged rod, the electric field is just equal to this. You don't need a sine theta because see, if this rod goes on for a couple of miles like that, that theta gets bigger and bigger, and eventually that theta becomes 90. And the sine of 90 is 1. So that sine theta term disappears if the rod's long enough. And then we did the electric field of a ring of charge. We derived this from scratch. We got all of these from Coulomb's law. Here's Coulomb's law, and we're getting all of these from Coulomb's law. And this one was you probably remember this. It's in your chapter. You could read it in your chapter. But that's, we derived that from scratch. The electric field of a charged ring. Remember, we had a charged ring. Now, we had a positively charged ring. If you had a negatively charged ring, and you came out here on the axis, the electric field would be going to the left instead of to the right. And it would equal this. Now this A is your distance here. That's your, well, you could put an R there if you like for radius, if that'd make you happy. And X is this distance here from the center to wherever it is you want to get your electric field. And then I think it was last Tuesday night, I showed you if you took a whole bunch of rings and you integrated, I took a whole bunch of rings. Uh-oh, it's getting kind of messy there. What you wind up with is a plate or a disc of charge, or a sheet. You could call it a sheet of charge. And the electric field for a sheet of charge, now it has to be big, because if it's small, it's a little more complicated. But if it's a big enough sheet, the electric field is equal to this here. There you have it. Where now this sigma is a charge density. I told you guys about 3 types of charge density here. Let me remind you. There's lambda. That's linear charge density, and what that is coulombs per meter. And then there's this little sigma thing here, and what that is surface charge density. And that's coulombs per square meter. And then we'll encounter tonight, I believe, I might have mentioned it, there's a Greek letter rho that's volume charge density, and it's coulombs per cubic meter. Now all of these we got from Coulomb's law. And in fact, some of these took us a while. I think this one here I derived using some calculus. There was a bunch of steps and a bunch of calculus there, but you understood it okay. And the same with well, the same with all this. It's kind of hard. But see, all of these can be done with Gauss's law. I need to tell you how to do Gauss's law. Okay, well, we've got a great group here. Let me see who we've got. We've got Zach and Stephen, Phoebe, Nicholas, Joshua, and Christy, Daniel, Jacob. Pretty good crowd. Okay, well, let's we had a review, and now when we mention some of these here in a little while, we'll show you how to get them with Gauss's law. Okay. Well, let's explain what flux is now. All right, here, I'm going to erase all this stuff. It's all wonderful, but we need to learn about electric flux. Now, before I do, let me just refresh your memory about dot products of vectors. If you have a couple of vectors, my phone's ringing. I don't really want to talk to anybody. Hey, Joanna, I'm right in the middle of teaching online. Can I call you back? Yeah. Say hi. Say hi to my. Say hi to my class, Joanna.
Hello, class.
Hi, Joanna.
Yeah, class. Say this is my daughter, my young. What is it? 51? 51-year-old daughter. Say hello.
That's right.
Say hello to my 51-year-old daughter.
Hello.
Hello.
Hey, you got two hellos out of that. I'll talk to you later, okay? Love you.
Okay, love you,
Bye-bye.
Dad. Bye.
Yeah, okay, there we go. Oh, yeah, I was going to review briefly what happened to my. I put an A dot B there, and what happened to it? It's underneath this picture here. I got to get rid of this picture. Yeah, there it is. Let me move it over to where it shows up. I've got some kind of little black rectangle there. Now, this is called a dot product. Now, in vectors, they call this a dot product. And you should all be very familiar with the dot product. There's another name, they call it the scalar product. And some books call it the inner product. But I like the term dot product. And I tell you what it's equal to. It's equal to this. Now you have to know that these are vectors. See that's a vector symbol. So that's vector A. This is your dot product. That's vector B. But this right here, that's not a vector. What do they call it when it's not a vector? Somebody? I need a little help here. Let's go to my friend. Let's
Magnitude?
Go to, say that
Christy says a
again.
magnitude.
Yes, it's the magnitude. This is just the magnitude of vector A, and this is the magnitude of vector B, and this is the cosine of the angle between them. And we'll need to do that because, see, electric flux, let me show you the equation for electric flux. Electric flux I don't know why they picked this symbol. This is a Greek letter phi. And let's see, alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, z, omicron, pi, rho, sigma, tau. I think I goofed up. Phi is towards the end anyway. Epsilon, phi, chi, psi, omega. Yeah, it's like the 20th or 19th or 20th letter of the Greek alphabet. And what it is, it's a dot product of your electric field and your area. So, but now these are vectors. You know electric field is a vector. You know that electric field is a vector, but you might not be familiar with area being a vector. They made a vector out of it. What they did was they took an area, like maybe here. Let me take an area. Here we go. We'll just take a square. I don't know. What does that look like to you? Maybe 0.10 meters, 0.12 meters. And so the magnitude of this area would be, if it was, well, it's not a square, doggone it. Let's go with 0.12 meters, 0.12 meters. Now it's a square. And what you'll get for the area, I could almost do that in my head. Is it 0.0144? Did I do that right? Let me see here on my calculator. By Jove, that's what it is. It's 0.0144 square meters. But see, that's not a vector. That's just a magnitude. That's a scalar. See, there's scalars and there's vectors. But you can make a vector out of it, and here's how you do it. You draw a perpendicular like that. Make it perpendicular to your area. There we go. Now we've made a vector out of our area. And that's how, if you take the electric field and you multiply by the area, you've got what they call electric flux. Now in case the electric field varies over your area, you have to use calculus. And in that case, the electric flux is equal to the integral of E dot dA. See, if the electric field is constant over your whole area, you don't need no stinking integral. You just go E times A. Okay, well let's do an example. So suppose you had an electric field. We'll make an electric field here equal to, I'm just making this up, 12 microcoulombs. No, that's not right. 12 newtons per, I'll get this right in a minute. 12 micronewtons per coulomb. There you go. Suppose you had an electric field like that, and you wanted the electric flux going through this area. Well, it would equal 12 micronewtons per coulomb times 0.0144 square meters, like that, times cosine. In this case, though, it'd be the cosine of 0 because they're parallel. See, the electric fields are going this way, the area vector is going that way, and there is an angle between them is 0. And here's our electric flux. Let me do it. Here goes 12 e to the minus 6 times 0.0144. It's equal to 1.728 times 10 to the minus 7 newtons per coulomb. Ta-da, we did it. We found the electric flux. Now you can make that fancy-wancy if you wanted to. Let's see. If you made that a minus 6, that's making that bigger. You'd have to make this smaller. And you could say micronewtons per coulomb. It's the same thing. Or if you wanted to make that a minus 9, you could do that. That's making it 100 times smaller. So you'd have to make this 100 times bigger. You know what that would be? That would be nanocoulombs, newtons per coulomb. All those are the same thing. And we've just figured a electric flux. Now you can have hundreds of different kinds of flux. Like hydrologists, for instance, could have a velocity flux. Put a little v there. And what that would be, instead of having electric field, they would have the velocity maybe in the river, okay? Well, what's our river that goes through Tulsa? It's the, don't tell me, I know what it is. The river, it's not the Colorado River. Right now my mind's blank. Now help me now. What's that river that goes through, Zach, what's that river that goes through Tulsa? Unmute.
The Arkansas.
Say it again.
The Arkansas.
Yeah, there you go. Zach knows what the river is. It's the Arkansas River. And you can have a velocity flux. See that's a velocity vector right there. All you need to know is an area that you want to talk about and the velocity of your river. But you also need the angle between the velocity and the area. Or you could have any vector of your choice. There's hundreds of different kinds of vectors out there. But now you know what flux is, and you know what electric flux is. Any comments or questions before we talk about Gauss's law?
The integral.
Just unmute and tell me if you have a question. We'll talk about Gauss's law.
When do you need the integral?
Say that again, please.
When do you need the integral?
Oh, okay. Let me see if I can show you an example of that. When you would need the integral, trying to think of a simple, good example of that. Now, who's asking me? Tell me your name.
Zach.
Zach, it's Zach. Zach is asking me. Well, suppose the electric field it's possible that you could have an electric field like that that's stronger up here at the top, Zach. See that it has a strong electric field, and down here at the bottom, it's weaker. The electric field is weaker. So you'd have to integrate that. You could write an equation, I bet, that would describe how that gets smaller there as a function of y, maybe. We won't do it, but see,
Okay.
if that electric field varied, it's not constant. You would have to put in that function of your electric field. In this case, it would be with respect to the y-axis because it gets bigger as the y gets bigger, and you'd have to integrate it. Now, the area that you would pick would have to be an area like this. See, there's call it dA, okay? And you'd find the flux for a whole bunch of little areas dA. And did that kind of answer your question there, Zach?
Yeah, that was clear. Thank you.
Yeah, okay, good. All right, well, let's do this Gauss's law, that thing here. Here we go. All right. Now Gauss, he came up with his law, and it goes like this. Now you recognize this part of it. That's just flux, but something's different here. They've got a circle there. Now what that circle means is you're going to take the flux of a closed surface. It's got to be a closed surface. And the flux of a closed surface is equal to the total enclosed charge divided by your beloved, well-known fundamental constant, permittivity constant for electricity. An example of a closed surface would be maybe a basketball. Do basketballs have deals like that, or is that a softball? Anyway, if you have a charge enclosed in there, I can't draw a basketball very good, but you got the idea. A basketball is completely enclosed surface. That's what the circle represents. And let's just apply Gauss's law to a basketball. Only if there's no charges in here, then this charge would be zero, and so there's no electric field in here. But let's do one that's more interesting than that. Let's put a positive charge right here. Here we go. And let's make it, just make up something. Let's say it's 8 microcoulombs. Okay. Well, we know what the electric field is from Coulomb's law for point charges. We had a little review here when you first logged on. But this electric field is equal to K Q over R squared. We need the radius. Now, I don't know what the radius of a basketball is. I should go get one, I guess, but I don't know. They're about 6 inches or something like that, which would be about
4.7 inches according to Google.
Okay, thank you so much. That's about 19 centimeters. We want to use centimeters, it's a lot easier to work with. We all know what K is. This is 8 microcoulombs. And what did I just say for centimeters? What'd you say? 4 point what?
4.7.
Yeah, 4.7. That's about 18 and a half. No, that's not right. Let me get this straight here. Just a minute.
It's
I'll have
inch.
this. 4.7.
Inches.
Yeah, that's inches. But now in
What symbol is that right after the K? Is that an 8?
that's an 8.
Okay.
Thank you for asking. My writing isn't that great, but that's the enclosed charge inside. Now I figured out that's around 11 centimeters, but you have to have it in meters and you have to square it. Okay, hey, we can get the electric field if you had that charge inside your basketball. Let's go ahead and get that. Get your calculators, do this for me, and tell me what the electric field is. It's rather humongous, actually. I'm getting 5.94 meganewtons per coulomb. But I'm going to wait till I hear at least 2 uh-huhs. I'm waiting for an uh-huh. Unmute and say uh-huh if that's what you got. If not, I'll do mine over. Did I get that right? Plug this in and see if you get what I got.
Yes, sir.
Yay, there's one. I need another one. Now, Chrissy just had a chat, but I didn't get to read it in time. I was looking someplace else. Let me see.
It said that's what I have. You got the same?
Oh, Phoebe says I'll be driving home, so I won't be able to respond. That's okay. We'll put this on YouTube. Christy
Yeah, I have that.
says something about magnitude, and she says that's what I have. And somebody just said something. What was that?
I got that answer.
Yeah, we're doing great. Okay. Now let's do it using Gauss's law. That was not Gauss's law. That was a form of Coulomb's law. But to use Gauss's law, we're going to take the E, it's constant. You can pull it out. And what you have left is the area of your basketball. And you don't need to worry about the cosine because the area vectors are all going in the same direction. And so you have a cosine of 0 term everywhere. And the area, the surface area of a sphere, in case you forgot, is 4 pi r squared. If you don't believe me, we could look it up in the appendix. There's an appendix in your book that has mathematical equations. But on the left side of Gauss's law, we have E times the area of your basketball equals the enclosed charge divided by epsilon 0. Okay, now what we're going to do is we're going to solve for the electric field. Take 8 microcoulombs, divide by epsilon 0, divide by 8.854 e to the minus 12. And then you have to divide by, to get the electric field, you'd have to divide by 4, divide by pi, and divide by, well, the radius is 0.11. This is 0.11 meters. You'd have to divide by 0.11 squared. And here's what you'll get. You'll get 5.94 meganewtons per coulomb. How about that? We got this value by using Coulomb's law. Ta-da. We got this value by using Gauss's law. Did I lose anybody, or is everybody okay so far?
Good so far.
So far, hey, good. Good deal. Excellent. Well, I'll show you something kind of interesting. Now, a basketball is made out of, I don't know, plastic or rubber. It's not made out of metal. I know that. But if you have a metal, here, let me just erase all this stuff here for just a minute. If you had a metal sphere, okay, here's a metal. Yeah, sometimes on cartoons they'll draw a kind of a soap bubble thing to give it 3 dimensions there. And if you charge that sphere up, it turns out that if it's metal, all the charges will go to the outside. There won't be any inside, because if there was, they repel one another. You know, positives repel one another, and they all head to the outside. So what you have is on the outside skin here, you got a bunch of pluses, but inside there's no charge. Outside there's charges on the outside. It's kind of hard to draw 3 dimensions. But inside, the enclosed charge is 0 because they all repelled one another and they went to the outside. Okay, now we could apply Gauss's law. Let's do that. Let's apply Gauss's law to this sphere that you've charged up. And now, one way to charge it up would be just to, I don't know, take your comb and run it through your hair and touch it, and that would charge it up. But not on the inside. There's no charges inside. So to use Gauss's law, which we know and love now, or we will, I hope, it goes like this. You have to make what they call a Gaussian surface. And in this case, we're going to make a Gaussian surface just inside the skin of our sphere, just inside the skin. And there's no, if that's going to be our enclosed surface, there's no charges inside. So on the right side of Gauss's law, we have a 0 for the charges, and Gauss's law looks like that. Well, you got 0 on the right side. On the left side, it's going to be 0 too, but it can't come from the area because a sphere has area. We know the area of a sphere. The surface area of a sphere is 4 pi r squared. And don't get mixed up. The circumference of a sphere is 2 pi r. And the volume of a sphere is 4/3 pi r cubed. Now these are all for spheres. That's different than circles. See, the area of a circle is pi r squared. There you go. Or you could go pi over 4d squared. That'd give you the same thing. You could look these up. You should have those memorized. But anyway, well, back to this. Something's zero on the left. And it can't be the area because the area is not zero. It has to be the electric field. The electric field is zero inside a metallic. Doesn't even have to be a sphere. It can just be a closed surface. As long as it's closed. It doesn't even have to be solid. Here, let me see if I can show you that. It could be a shell. You could have a spherical metallic shell like this, and if you charge that up, all the charges will go to the outside because they will repel one another. And what I told you about the sphere is true for a metallic shell. Or what would be a better name for it? A spherical shell, maybe? I don't know. And the electric field inside a closed metallic container, like a box even. The electric field is zero. This was first demonstrated by a guy named Michael Faraday in 1843. He did an experiment. His name was Faraday. And it came down to us. It's known as the ice pail experiment. You could look it up. Go to your search engine and just type in Faraday's ice pail experiment, and there'll be YouTubes and all kinds of Wikipedia stuff about it, telling you all about it. And what he's saying is there's no electric field inside a closed shell. Now I want to demonstrate that. We're going to have an experiment now. I'm going to do my version of Faraday's ice pail experiment. Now for a radio to work, I've got a radio here. I wonder if it's charged up. Let me see.
And I put this in the newsletter last night.
Yeah.
So this came out.
It's working.
The press was bringing up QAnon because
Can you
really
guys hear that?
wanted something to focus on.
Yes,
Because
sir.
run
Yeah.
from the fact that these are Democrat cities and all of this is happening in Democrat cities. They couldn't get away from it.
There we
So
go.
they decided to
I've got a radio here, and I'm going to put it in a. Well, I just got some tinfoil. I'm going to put this radio in this tinfoil. Well, here goes. Now you watch. I'm going to turn this thing on.
that was the whole thing. So then Trump gave us pressure.
Let me turn that up. This is one of those crank radios. Let me crank it up.
That noodle, when they threw it against the wall, wasn't sticky. So they had to pivot to something else.
Now
And I
now
said,
I'm
"If you're
gonna
looking for something
I'm
else,
gonna put it
they were
inside a
looking for something
metallic
else to seize on."
closed
But I didn't
surface.
know if it was, because it seemed like the Rittenhouse thing for the most part, right? Was out of the press, right?
Whoa! What happened? Here, let me open it back up.
Because that's probably who we're charging. So then they
See, radios work on electric fields that oscillate back and forth,
press conference yesterday.
but inside here, there can't be any electric field. according to Faraday's ice pail experiment, there's no electric field. Now there's a little bit, I can barely hear it coming out the end here, but I could close that up. I can close up this end. And now it's supposed to be completely silent. I think I still heard something. But if you open it back up, see there? Okay, well, let me turn that off.
So the whole point of the experiment is just to show that there's no electrical field inside of something
There is
enclosed.
no electric field inside of a closed metallic. It's got to be completely closed. It's called the Faraday's ice pail experiment. Okay, well, I've shown you Faraday's law. Let me show you, no, I've shown you Gauss's law. We don't learn Faraday's law till a little later. But I did show you Faraday's ice pail experiment. Let me just show you, when you first tuned in, I had a little review of some basic things that we've studied. One of them was this one here, the electric field of a long rod, a long charged rod. If you have a long charged rod, and we derived this. It took us half an hour. Yeah, there's the equation. 2k lambda over A. We derived that from Coulomb's law, and you probably take excellent notes. You could go back, I don't know, it might have been time before last, I don't remember. But we had to use calculus to get it. But let me show you how you could get that using Gauss's law. And it'll be easy. See, with calculus, man, there was a bunch of steps, and we had to take an integration.
I actually have a question about that. I have two different versions of this now. I have a long one for the for the long charge. I have one with the ×2, and I have one without it. How do you tell the two?
There's a long rod and a short rod. Is that what you're talking about?
No, I have two long rod equations with the 2 multiplier and without it.
Oh, you have two different long rod equations.
Yeah.
Like well, there's only one. There's only one. This is it.
The one you wrote on the board earlier didn't have the 2 in front of the K.
Oh, I didn't? Well, that was a mistake. Okay. If I didn't have a 2 there, it was wrong. Is that my friend Zach?
Yeah.
Zach, and the rest of you guys, this is the equation for a long charged rod. And
I seen that in the book too.
Yeah, it's in the book. And if I didn't have that 2 there, it was wrong.
All right.
Zach, I'm gonna give you a thank you point. I appreciate you guys staying awake and helping me if I do a silly thing like that. Now we're going to do the same thing for a long charged rod. Now here it is. Here's your long charged rod, and it needs to go on for, I don't know, miles, but it keeps going is the basic idea. Now to use Gauss's law, you have to make a Gaussian surface. And what I'm going to do is I'm going to put a cylindrical Gaussian surface There we go. I think this needs to go, yeah, like that. Our artist's rendition there. You could put some dash lines there. Yeah. Now you can see it's a cylinder. Now you know that there's an electric field that's doing this everywhere. It's in 3 dimensions actually. But there is no electric field going horizontally. It's all going out away from your charged rod. Now let's do the area vectors. See, if you put a little area vector here, there's an area vector, dA. They're all going parallel. They're perpendicular to the cylinder, but they're parallel to the electric field. See, these are the electric fields, and these are the area. Here, let me write the Gauss's law here for us. This is, remember, the enclosed charge, and this has an area vector, but it's at 90 degrees to the electric field. And you know, when you do a dot product, you have a cosine, and the cosine of 90 is what? What is the cosine of 90? Somebody tell me.
0.
Cosine of 90 is
0.
It's 0. It's 0. So you don't get a term for these 2 end pieces. There's actually 3 areas here. There's this area here, which is equal to, say this is the length of your cylinder. It's equal to the length of your cylinder times the circumference, which is 2 pi r, or make that distance a. That'll be good. That's the area, and there's the electric field. There's the left side of Gauss's law. We have your electric field. You have the area, which is the length times the circumference, 2 pi a. There's a cosine of 90 in there. No. There's a cosine of 0 for this part here. These here have a cosine of 90. They don't contribute to the left side of Gauss's law. And here we're going to have the enclosed charge, which will be lambda times L. Remember, lambda is the charge per length. And if this length is L, if you got a length of L here, and you have the charge per length, and you multiply by the length, you'll get the charge that's inside the closed Gaussian surface. We just did it. That's it. Now let's solve for the electric field. Well, algebra-wise, you can get rid of those L's, and you'll have lambda over 2 pi epsilon 0a. Algebra students, can you get from here to here? Can you make it?
Yes.
It's just algebra. Now we're going to do a little algebra trick now. We're going to multiply the numerator by 2 and the denominator by 2. That didn't hurt anything. It's legal to do that. It's just that K is equal to 1 over 4 pi epsilon 0. And so this is equal to 2K lambda over A. We just came up with this formula in 3 steps. 1, 2, 3. If you took notes the night we derived this equation from Coulomb's law, there was a whole lot more steps involved. And we had to integrate. I think I had to go to an integral table to get it, to solve it. It was a little bit nasty. I don't want to do it again tonight, but hey, we just did this equation using Gauss's law. Okay, any comments or questions? Okay, well let's do another one of our equations with Gauss's law. Here we go. If you're happy with that, I'm going to erase that and do another equation with Gauss's law. All right, nobody said anything. We'll say goodbye to that, and I'll do another one here. Now, another equation that we came up with. Yeah, I remember it. We took a bunch of rings. And we made the rings bigger and bigger and bigger and smaller and smaller and smaller. And we made ourselves a sheet or a disk or a plane of charge. And it turned out that you have an electric field for a sheet of charge doing this. And it's equal to sigma over 2 epsilon 0. And again now, that was really hairy. We had to use an integral table, and it was nasty. But if you took notes, you have that someplace, or you could read the book. You could read the book. There you go. But let's show you this equation using Gauss's law. Okay, suppose you had a big sheet of charge. Just make it really big. And we're going to put a Gaussian closed surface here. It's kind of hard for me to draw that, but I tried. And we know there's an electric field going like this make it a positively charged sheet of charge. Now this time, this area here around the circumference doesn't give you any electric field because the area vector, dA, at any point on there is perpendicular to the electric field, and the cosine of 90 is 0. This time, Gauss's law, the electric field and the area vector, dA, are parallel only on the end pieces. So when you do Gauss's law, you're going to have a thing like this. But there's two of them. So there's two areas. Call this area A. There you go. You're going to have E times A, but there's two of them. So you've got two areas equals the enclosed charge divided by epsilon 0. Well, see, the enclosed charge is equal to the charge per area times your area. So this is equal to sigma A over epsilon 0. Now we're going to do some algebra. I think we can get rid of those areas, and what you have left is E is equal to sigma over 2 epsilon 0. Can you see that? Because the areas you can cancel. Divide by 2, and by Jove, you've got, you've got the equation that took us, I don't know, a dozen steps and some integral calculus. We did it in 3 steps. 1, we started with Gauss's law. 2, we had to figure out the area and the enclosed charge using this charge, surface charge density. And 3, by Jove, we're done. So Gauss's law is pretty nifty. It can give you some results in a hurry. I might have gone too fast on that. Does anybody have any problems with that? I want me to go back over it slowly? Just go ahead and ask if there's a problem. Well, I guess there's no problem. We're going to work some problems now. If you're happy with that.
I think I'll know if I understand when we work some problems.
Now tell me your name.
Jacob.
Jacob is saying that he thinks he'll get it after we do some problems. Is that what you said, Jacob?
Yes, sir.
Yeah, I agree. I think you will. Okay, well, let's work some problems. Why don't we do, we'll start with this one. We're going to do problem 624. It's in your book. Let me erase all that. And let's find that. Let me get my book out here and see what it says. If we have time tonight, I'd like to gently introduce some stuff in chapter 7 because I think your test a week from Thursday is 5, 6, and 7. Yeah. Well, we'll see. We might not have time. Okay, now let me find this 624. Just a minute. I'm shopping around here. And there it is. I think I found it. Yeah, there you go. 2 large rectangular aluminum plates of area so-and-so, 150 square centimeters. Well, they're square. Well, maybe not. They're rectangular. Doesn't matter. If they were square, what's the square root of 150? See, a square is a rectangle, you know. All rectangles are not squares, but all squares are rectangles. And it's 12 centimeters on the side. Okay, we'll do that. We'll have 12 centimeters. Well, really, it's 12.25 centimeters. Trying to get a handle on a handle, not a hangle. Trying to get a handle on this thing here. But if you did that, you would have 150 roughly square centimeters, wouldn't you? Somebody double check me, make sure I'm not lying to you. Now they're facing each other with a separation of 3 millimeters. Well, now that's 12 centimeters, right?
Christy says that's correct.
Good going, Christy. Did she chat? Did she send a chat to us?
Yes, sir.
I haven't got the hang of these chats yet. Okay, now the separation is 3 millimeters. Okay. Well, gosh, that's really close, isn't it? I was going to do this to scale, but these babies are just very close together. I don't think that was very good. Let's do it like that. Yeah, this little tiny distance right here is 3 millimeters. They're terribly close, aren't they? Because see, that's 122 millimeters, isn't it? And they're just 3 millimeters apart. Okay, now we're going to charge them up with 20. We're going to make this one plus 20 microcoulombs. We'll make this one negative 20 microcoulombs. Okay. And the plates face each other. Find the flux through a circle of radius 3 centimeters between the plates. Well, man, that's kind of hard for me to draw. It's got a radius of 3 centimeters. Well, it's 3 centimeters will put you about, I don't know, about there you go. There's your 3 centimeters. It's kind of a goofy problem, but I didn't write this book. Hope you can read my writing. You've got a radius of 3 centimeters. It's in between the plates. There's not much room in there for it. It must be a skinny, very thin circular plate. They want the flux through a circle of radius 3 centimeters between the plates. But it's at an angle. See, now you always measure the angle, the area vector. There it is. You measure that. They said it's at 5 degrees. Here, let me tilt it just a little bit. There we go. There's your area vector. Now, the electric fields, though, I can put them in red. They're going like this, from positive to negative. But there's a teeny tiny angle. There's a teeny tiny angle between the area vector of that 3 centimeter radius circle and the electric fields. And we know what the electric field is of 2 equal opposite plates. Now for a single plate, the electric field is sigma over 2 epsilon 0, but that's just for one plate. Now if you have 2 plates like this, they add up, because 1/2 plus 1/2 gives you 1. You get this here. This is I think I've shown you this before. The electric field inside that, what that is a great big capacitor, which we will be studying down the road. We can get that because we know what the sigma is. The sigma is 20 microcoulombs divided by, I don't want centimeters. Here, multiply this by 1 meter over 100 centimeters and square it. And what you'll get is 150 divided by 100 squared. I'm getting 0.015 meters squared. That's what you have to have in the numerator, 0.015. Okay, now that's your surface charge density. And you know this here by heart, 8.854 times 10 to the minus 12 Newton meter squared per coulomb, I think. I think that's what it is. Let me double check. I don't want to lie to you guys. It's nope, that's wrong. It's Coulomb squared per Newton meter squared. I'm glad I checked. Okay, no, I got lost. We're doing 624. What are we supposed to be doing here? Let me read this again. And the charges on the plates, the flux. Find the flux. Okay, we're going to find the flux. Well, here, let me write the equation for that. We're going to find the electric flux through this circle. And it's equal to, in this case, EA, it'll be cosine of 5 degrees. And now, here's our E, and the A, that's our A. Okay, let me write it. You got 20 microcoulombs divided by blah, blah, blah. Divided by epsilon sub 0. Okay. Times the cosine. Now, wait a minute. I need the area. Well, now I need the area of the circle, not of the whole thing. The area of the circle is pi 0.03 meters squared. Pi r squared, right? Yeah, pi r squared. Cosine of 5. Yeah, there we go. See, here's our, what do they call that? Surface charge density. It's the charge over the area. I did that. Wait a minute. Auga, I need a 2. Did I forget my 2? Yeah. See, I was going to get this wrong. You have to have a 2 there. No, you don't either. No. We got 2 plates, and so this is our electric field. There's no 2 there. That was when you had just 1 plate, but we have 2. So there you have the that's the electric field. All of this is your electric field. Okay. Probably should erase that. That just confused me there. And there's your area of your circle, and there's your cosine of 5. I want you to put this in your calculator, and we're going to get the answer. Go ahead. I will shut up for a minute. Plug all of this in your calculator, and we're going to get the electric flux through that circle. Go for it. Well, I got an answer. Let me go to some of my wonderful students here. I wonder if anybody's got that. How about my friend Stephen? Stephen, did you plug all that stuff in and get an answer yet?
I did. I got 2.827 e to the 7th.
Here, let me write that down because it might be right, Stephen. It's not what I got. You got 2.827?
Yeah.
Times 10 to the 7th? How about somebody else? How about somebody else? How about maybe Phoebe? Phoebe, did you get that yet? This was Stephen here. We'll put his name on it. Phoebe's not going to answer me. Or maybe she's still working on it. How about Joshua? Joshua, do you have that yet?
I'm still working on it.
That's fine. Yeah, take your time. Uh,
I got four,
let
two,
me
four.
find my other friend there. Jacob.
Yeah. Got the same as Zach at like
No.
0.424 mega.
Yeah, or no, my
Uh,
no.
Okay, now who am I talking to? Is this Jacob?
Yes.
And tell me what you got, Jacob.
424.165.974.
That's what I got. That's what I got. And you said somebody else got that?
Zach got the same.
Yeah, I got that.
Well, that's what I got. Now, we got to put the units in there, Jacob and Zach. What are the units of
Wait,
electric flux? Anybody know?
point
Had it
four-
written down.
4 coulombs.
Well, it'd be the units of electric field times the units for area. Well, what's the units for electric field?
Newton Coulomb.
Newtons per coulomb. What's the units for area?
Meter square.
It's just meters squared. So it's Newton meter squared per coulomb. Okay, well, let's look in the answer book and see how we did. This was problem 624. Oh, gee. I don't know if they have answers for even problems. No, they don't. But I have an answer book, and let me tell you what the answer book says. We'll see if we got that right.
Mhm.
Here's what the answer book says. They said 424 kilonewton meter squared, kilonewton meter squared per coulomb. You know what? I think that's the same thing as what we got. See if
Yes,
you
sir.
see they just lopped off the 165 and made it a kilo. Yay, we did great. We did that. Anybody need more help on that one?
I'm sorry I didn't respond. I wasn't able to.
Well, that's okay. That's Phoebe, right?
Yes, I'm sorry. I just got home.
Oh, that's fine, Phoebe. Don't just drive safely. That's what we care about. And you can watch this first part on YouTube. I'll get my daughter to put this whole session on YouTube, and you can watch it. That'd be great. But what we did problem 624, and we got the answer in the answer book. Was there any other comments or questions on anything? If not, we'll just work. We're going to work some more problems. Okay, well, let's work another problem then. Here we go. Let me erase all this stuff, if you guys are happy.
Yes, sir. Go ahead.
Okay, now when you guys do your problems, make a sketch. See, I tried to draw a sketch, and I want you to make a sketch. Some of you aren't doing the sketches. I think they're important. All right, we're going to work some problems. We've learned about electric flux. Now this is problem 625. There we go. Now let me look it up and see what it says here. Having trouble writing a 6. Okay, it's 625. And it says a square surface of area 2 square centimeters is in a space of a uniform electric field. Okay. The amount of flux depends on how the square is oriented relative to the direction of the electric field. Before I do this problem, let me tell you about when you watch a submarine movie, World War II. You know, they have a submarine and a destroyer,
Yes, sir.
and here's the destroyer. Okay, there it is, and it's got there's the destroyer, and it's going along here like this, and there's a submarine over here, and they send some torpedoes. The enemy below with Kurt Jurgens, and who is the skipper of the submarine? Oh gosh, can't think of his name. But see, they send these torpedoes, and here they come. And the captain gets on the bullhorn, auga, auga, left full rudder, give me emergency speed. And see what he wants to do. He wants to turn his ship so that it's pointed this way. Yeah, here's his destroyer now. And so he turns his ship so it's that way, and here comes the torpedoes, and they go skimming by, and they just miss. They don't hit the destroyer. It's very similar to flux, only this isn't electric flux. It's well, it would be velocity flux, really, because these torpedoes have velocity. And in the movie, the sailors all look over the side of the ship, and they see those torpedoes about 20 yards away, going parallel to the ship, and they think, man, that was close. That was close. See, what you don't want is when you're on a destroyer is to be pointed this way, and here's your destroyer, and here come the torpedoes. That's bad news, because they'll hit your ship like that. Okay. So what's that got to do with this? Well, I don't know. Let's see. We're doing problem 625, and we're going to draw the square surface area of 2 square meters, and it's in a magnetic field. Or we're not doing magnetic yet. We'll get to that. It's in an electric field equal to 10 to the 3rd newtons per coulomb. Okay, and the square surface area is 2 square centimeters. But it depends on how the square is oriented relative to the direction of the electric field, kind of like the destroyer and the torpedoes. They want us to do this when the normal to the surface, the square, makes an angle of 30 degrees with the electric field. Okay, I think what they're talking about is if you have your square oriented kind of like this. It's kind of hard for me to draw that, but I'm trying. And see this angle here. Now wait a minute. No, no, I did that wrong. Let me read it again. The normal to it makes an angle of 30 degrees. Okay, that's more like this. See, here's the normal. That's your area vector. Remember, area vectors are always perpendicular to your area. Now here comes the electric field, and here's the angle here. For part A, that angle is 30 degrees. The normal to the area is the direction of your area. Okay, now what are we supposed to find? It's weird now that find. They want the electric flux. Okay, here we go. We're going to find the electric flux. What that is it's E dot A. You don't need to integrate anything. And the E we know. Let me circle it. We know what it is. It's 10 to the third newtons per coulomb. And the area we know it's 2 square centimeters. I don't want centimeters. I want meters. So I'm going to do this. There's 100 centimeters. Here we go. Now, if you'll do that with me, we'll get the area in square meters. I'm getting 2 times 10 to the minus 4 square meters. And now we got the area. Look at us. We got the area. So here, let's write this out. We have 10 to the third newtons per coulomb. We have 2 times 10 to the minus 4th square meters. And then we have cosine. It's this angle here. It's cosine of 30. It's the angle between the area and the electric field. Okay. And now I'm going to do that on my calculator. And let's see if you guys can get the same answer as me. Go ahead. I'm going to do it. You do it too. Well, I got an answer for the electric flux. And we'll go to one of my wonderful students. Let's see here. Let's go to my friend Daniel. Daniel. Unmute, Daniel, and tell me what you got for the electric flux. Earth calling Daniel. Come in, Daniel. Well, Daniel's busy. Christy, I know you're with me. Christy, you won't let me down. Well, what'd you get when you did this, Christy?
She got 3.09 times 10 to the negative second.
3.09 times 10. Well, that's not what I got. I could be wrong. Let me do mine over again.
Did you get a ridiculously small number?
I got 866.
Uh,
I did it wrong then.
well, let me do mine all over again. Here we go. No, I got the same answer twice. I didn't get either one of these. How about another one of my friends? How about
got,
Nicholas?
like-
Go ahead.
I got like some 0.173205 number.
That's what I got. I got 0.1732 Newton meter squared per coulomb. Now let's look and see if that's the right answer. Well, there's a part B and a part C. We'll get to those. Let's just see if we got that part right.
Got now.
We're doing 625, and I'm going to see what the answer book says for part A. 625. 625. I need to be in the right chapter. Okay, for part A, they said, the book says 0.17 Newton meter squared per coulomb. They're just kind of lazy and they rounded off. I think we got the right answer. We did great. Y'all, a little Southern talk. Y'all happy with that now?
Yeah, I'm good.
Good.
And the 2 centimeters was part of the problem, right? Like from the given.
Yeah, see that's now this is wrong, guys. That's 2 square centimeters, isn't it? I didn't put a little 2 there. Shame on me. On 625, it's 2. I didn't have that little 2 there. If I make a mistake, I need you guys to tell me. But I think it's correct now. All right, now that was part A. Let's do part B. Here we go. Now, what's part B? 90 degrees. Well, okay, let me draw this at 90 degrees. There's our electric field. And this time we're going to put our area this way. And see the area vector is not, it's 90 degrees to the area and it's 90 degrees to the electric field. And you're going to have a cosine of 90. What's cosine of 90?
0.
It's 0. So part A, ta-da, we did that. That was part A. Part B, let me make some room here. Part B, the electric flux. The name of that is called electric flux. And it's going to be 0 because you had a cosine of 90 there. See that angle there is the angle between the E and the A. Here's the A, here's the E. That angle is 90, cosine of 90 is 0. Now let's do part C. Read it. It says here the angle is 0. Okay. Well, let me draw that. See, this was, what I'm drawing here is part B. But part C, you got your electric field doing this. Part C, they want to have your area vector parallel to E. They want to have the angle between the area vector and the electric field to be 0. Okay. Well, it's going to be this times cosine of 0. What's the cosine of 0?
1,
Cosine, go ahead.
1.
It's just 1. So I'm going to do that now. I'm going to take this times that times 1. Here goes. Well, I got an answer for your electric flux of 0.2 Newton meters squared per Coulomb. And now let's see what the answer book says on that. Go back here, we'll see what they say. And now this is chapter 6. We're doing problem 25, chapter 6, and they said, oh, here we go. For part C, they got A there and then B, but where is part C? I got lost here. Well, they got an answer of 0.2. That's what we got, wasn't it? Yeah. Yeah, they never did say C, though, did they? Kind of confusing. But in the back of the book, in the answer book, they did have the right answer. It's 0.2. That's good. Yay. We did good. We got that under our belts, and we're going to do some more problems and have some more fun here in a little bit. But we're going to take a, I don't know, 8 to 10 minute break. You got time. You could go make yourself a peanut butter sandwich in 8 to 10 minutes. The beauty about this is you could eat that sandwich while we do the next problem. Okay, we'll be back. We'll be back in 8 to 10 minutes. Go, take a break. I need a break. You need a break. Okay, if I can stand up. Take a break. We'll be back. Okay. I think our 8 or 10 minutes is up. And we're just going to work problems here I wonder what we should do next. Let me look and see here. We just did 625. We could do this one. This is 651. Let's do that. This looks quick and easy. I like easy problems. Welcome back, everybody. Let me see who we got here. Oh, we got our good group here. Yeah. Got our good group. And let me erase this here. We're done with that. I don't want to erase that thank you point, though. Somebody got a thank you point for helping us. And stay awake, because I'm quite capable of writing the wrong number down. But I thought we'd do 651. Okay. All right, 651. Well, let me find it. Let me dig around here and find it. Chapter 6, number 51. Yeah, here we go. Okay, it says here the electric field at 2 centimeters from the center of a long copper rod of radius 1 centimeter has a magnitude of blah, blah, blah. Okay, well, let me draw it. Now, when you do your problems, draw a sketch of the situation. We have a copper rod of a long copper rod. So it's very, come on now. It's very long, yeah. And it's 2 centimeters. The radius is 1 centimeter of the copper rod. And see, this copper rod goes on forever, I guess. It's just very long. We just did part of it. And the radius is 1 centimeter. So if the radius is 1 centimeter, that means it has a diameter of 2 centimeters. And the electric field is 2 centimeters from the center. Well, that's going like this. Here's the center. And if you come down 2 centimeters, oh, come on now. Come on down 2 centimeters. See, here's the center of the rod. Okay. And then you're right here and you have an electric field. Did they tell us what it is? Yeah, they said the electric field is 3 newtons per coulomb. 3 newtons per coulomb. We've got an equation for long copper rods. It goes like this. 2, I think I forgot the 2 earlier tonight. 2 K lambda over the area. Now the area, what we want, not area, distance. We want the distance from here to the center. I think it's 2 centimeters. Yeah, it's 2 centimeters. So we have 2K, what's the lambda? The charge per, oh, they want us to, we're supposed to find it. We don't know what this lambda is, but we're going to find it, and this is 2 centimeters. It has to be in meters. But see, we know what K is, and we know what this is. We've got an equation here with only one unknown, and I can solve it. So here we go. We're going to solve for the, what do they call that? The linear charge density. Let me write that down. That's the linear charge density. And they want that, right? How much charge per unit length? Yeah, that's what that is. Okay. Well, get your calculators. Here's an equation with only one unknown. That's the lambda. A lot of times in this class, if I have an unknown, I'll put a little mystery cloud around it. I call that my mystery cloud. See, if I know something, I'll put a circle around it. But if I don't know something, I'll put a mystery cloud around it. Okay, let me solve that, and we'll see what we get. Here we go. Well, I did that. I wonder if it's what you got. I got 3.337 times 10 to the minus 12 coulombs per meter. Coulombs per meter. Okay, is that all we're supposed to do? Let me read this. How much? Oh, that's part A. What would be the electric flux? Well, we'll do that in a minute. Let's see how we did on part A. See, this was part A. Let's go to the back and see what they said for the answer is 651. They said the answer is 3.33. The book says 3.33 times 10 to the minus 12 coulombs per meter. Hey, we did pretty good. I think maybe somebody rounded off something. I don't know, but I'm pretty happy with that. Okay, let's do part B. Part B, what is the electric flux through a cube of side 5 centimeters situated such that the rod passes through opposite sides of the cube perpendicularly? Okay, well, we're going to draw a cube now, but it has side 5 centimeters. In other words, it's a little bit bigger cube kind of affair here. Here we go. I'm trying to draw us a cube. When you do your work, draw a sketch. And what do they want us to find? The electric flux. We're going to use Gauss's law. I need some room. There's some room over here. We'll do this. Okay, now Gauss's law says, Gauss's law. There's 3 S's in Gauss's law. Look at that. See the 3 S's? Gauss's law says you have to take a closed surface. It's called a Gaussian surface. Is that stuff showing up? Yeah, it's showing up. E dot dA, and that's equal to the enclosed charge divided by epsilon sub 0. Okay, now this right here is flux. It's the total flux. Is that what they want, the total flux? What would be the electric flux through the cube? Okay. This cube has got 5 centimeters on the side. 5 centimeters by 5 centimeters by 5 centimeters. We need to think about the This term right here, this is flux. That's what flux is. What this is the total flux leaving the cube. I think that's what they want. Read it. It says, what would be the electric flux through the cube? Okay, well, that's it. I tell you what it's going to equal to. It's going to equal the enclosed charge. Now, the enclosed charge is going to be lambda times the length. See, there's charges on this, and the length is 5 centimeters, so you go 0.05 meters. And if you multiply by the charge per length, you'll get the enclosed charge in your cube. See, there's charges out here, but they're not inside the cube. This term here on Gauss's law is the enclosed charge. Okay, well, that's it. Well, this should be the answer. All right, we've got the lambda. Let me circle it. We just figured it out. It's 3 point blah, blah, blah. It's right there. Put that in your calculators, divide by that, and tell me what you get for the flux leaving the cube. I'll give you a minute to do that. Go for it. Hi, bud.
Still teaching?
Yeah, they're trying to plug this into their calculator right now.
Oh. Whoa.
And
Is that a decimal?
yep, that's a decimal. Are you learning decimals yet?
Yeah.
Gee, that's pretty good for 5th grade. I didn't know they did that. Okay, guys, I got an answer. Let me pick on somebody here. Now here's a person. Daniel, I think I called on him already. Nicholas, I don't remember if I've called on you. Nicholas, did you plug in this lambda times 0.05 over epsilon 0? What'd you get, Nicholas? Earth calling Nicholas, Earth calling Nicholas.
Yep.
Yeah, what'd you get?
I ain't quite got it yet.
Oh, take your time. What we're after is this thing right here, Nicholas. It's called electric flux. And if you plug in those numbers, we'll get it. How about my friend Chris? Go ahead.
Did you get a small number?
Yeah, I got an answer. What'd you get?
0.01884459.
That's what I got. I got 0.0188. We'll quit with a 4. That's good enough. Now we need units. They're Newton meter squared per Coulomb. Now let's see how we did. This was problem 651. I want to see how we did. Go to the back, and we'll see if we got that right. Now, be warned, they're not always right. This book makes mistakes just like you and me. But they're usually right. They're pretty good. Okay, this is 651. They said the answer is, the book says 0.019 Newton meters squared per Coulomb. Hey, they just rounded off. We did great. Look at us. If you rounded it off, that's what you get. I'm pretty happy. And that's the end of the problem, isn't it? Yeah. Okay. Yay. And look, we drew a sketch. Yeah, that's what I want you to do. Any comments or questions on that one? That was problem 651.
Can you go back over how you got the lambda?
Yeah, thank you for asking. That's a good question. Now, this here is the enclosed. The word is enclosed. And what that means is it's inside. It's the charge inside. See, there's charges outside, but we don't give a rip about them. Just erase them and forget them. See these charges that are outside? We don't care about them. We only care about the charges inside. Now the charge per length is called lambda. That's the charge per length. What lambda is the charge per length. Well, the length is 5 centimeters. So if you want the charge, you take lambda times, well, you need to be meters, it'd be 0.05 meters. That's how I got it. It's right here. No, that's not it. I got lost. There's the lambda, and if you take that times 0.05 meters, you will get the enclosed charge. Now, who was that just asked me that?
Jacob, I was asking about how you got the lambda.
Yeah, Jacob, do you understand how I got the enclosed charge now? Or are you asking how I got the lambda?
I'm asking how you got the lambda, yes.
Okay, now hang on a minute. We did that earlier. I forgot how I got the lambda. Let me read it again.
Alrighty.
Oh, they gave it to us.
Oh, all right.
Didn't they? No, wait a minute. No. Here we go. I'm talking to Jacob, right?
Yes, sir.
Jacob, we've got this lovely equation that we've talked about tonight. E equals 2k lambda over A. They give us the E. They didn't give us the lambda, but they gave us the E. And now the A is the distance from the center of the rod to where they gave us the E. So basically what we're saying is they give us the A, they give us the E, we know what K is, so you solve for lambda, and that's what we got. Are you okay now, Jacob?
So you just manipulated it algebraically.
Yeah, right.
Okay.
Anybody else? Anybody else comment or question? Well, okay, let's do another one. If you're happy with that, we're going to erase it. Tonight we're studying electric flux and Gauss's law. Okay, let's do another one now. Which one do I want to do now? Let me think. Oh, this is a fun problem. They had a very long rod of charge. We just did a very long rod of charge. But here's another one. Very long rod of charge. There it is. And we'll make them plus. We'll make them pluses. There we go. Bunch of pluses there. There we go. Well, so what? What are we going to do with it? Well, we're going to give you the lambda. We're going to say that the lambda on this very long, it's very long, it goes on and on. I just don't have room to write it. The lambda we're going to say is 6 microcoulombs per meter. So we've got the lambda. Now, what we're going to do is we're going to make a Gaussian surface, a spherical Gaussian surface, and we're going to put it right here. Here it goes. We're going to make a spherical Gaussian surface. There it is. It's a sphere. This, here, let me do a little, like in the cartoons, they do that soap bubble thing to kind of give you that three-dimensional feel to it there. Let's suppose that the radius, let me find the radius of this. Let's say this is, say it's got a radius of 3 meters, okay? That's a pretty big sphere, isn't it? We have a sphere where the radius is 3 meters. And we have a charged rod that penetrates the sphere. And the distance to the charged rod is, let's say it is 2 meters. Okay, now what we want to know is, we want to know the electric flux leaving, we want to know the electric flux leaving the sphere. We're going to use Gauss's law. Now you could write this right here. That would be fine, because this is Gauss's law. But it would be awfully complicated to figure that. But it won't be awfully complicated to figure this. If we can figure the enclosed charge, you see this charge that's outside the sphere? It does not contribute to the enclosed charge. You can just dismiss it. Forget about it. It's not inside. You have a spherical, three-dimensional sphere, and you've got this rod that's penetrating it like that. We need to know what the charge is that's inside the sphere. Okay. Can you figure that? Can you figure the enclosed here? We'll put a little mystery cloud around it. I'm going to shut up for just a minute. I want to see if you can figure out the enclosed charge inside that sphere. We know the charge, the linear charge density. We know the radius of the sphere. We know the distance from the center to the rod. Can you figure the enclosed charge? I'll give you a minute. Go for it. I think I put the Thursday night's lab on content, but I'm not sure I did. Does anyone know, did I put the Thursday night's series parallel lab on content? Does anybody know? Anybody ever look at the content on Blackboard?
I don't know. I haven't looked.
That's okay.
Yeah, I've seen it. It's up there. It works.
I'm sorry, what?
So I've seen it.
It's there.
Yeah.
Good, 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 good. So study that when you come Thursday night. I'll make a few copies too in case you don't have a printer. Okay, we're going to find this enclosed charge. Now here's what we're going to do. We're going to take lambda and we're going to multiply by the length. See, lambda is charge per length. By length, what I'm talking about is this length here. It's how long that is. Well, how do you figure that? How do you figure how long? What it really is this length here, isn't it? From here to here. How do you figure that?
Pythagorean theorem.
Yeah, it's Mr. Pythagoras again. We love him. What you're going to do is you're going to take this distance here, which should be 3 squared minus 2 squared, square root, and then multiply by 2. So this should be 2 square root of 3 squared minus 2 squared times lambda, which is 6 microcoulombs per meter, and then divide by epsilon 0. Okay, see, this will be in meters, and the meters will cancel. And when you, oh, wait a minute, I'm doing something wrong. There's the lambda. There's the length. That'll give you the enclosed. Yeah, there we go. Now here's what you want. Once you get this enclosed charge, then when you divide by epsilon 0, that'll give you the flux, the electric flux leaving the sphere. Another way of thinking of electric flux is it's the number of electric field lines that are leaving the sphere. Maybe I can explain that better in a minute. But go ahead, figure the enclosed charge from this. Do this with me. Here we go. Okay, I got an answer for the enclosed charge. I'm coming out with that's just in coulombs. And then when you divide by epsilon 0, you should get the electric flux. That's you could think of that as the number of lines of electric field lines leaving the sphere. Okay, I'm going to do that now. Okay, here's what I'm getting. Now that's what I'm getting. I wonder if that's what yes, that is the correct answer. Oh, wait a minute. The units are wrong though. It should be meganewton meter squared per coulomb. There we go. Did I lose anybody on that one?
No, sir.
Good, excellent. Well, let's do another one. if you guys are happy with that, we're going to do another problem. We're just going to keep working problems till we get the hang of this stuff. I'm going to erase this if you're happy. Now that one was not in your book. I just made that one up. But wasn't that fun? This next one's in your book. We're going to do problem 644. It's in your book. Let me make a little room here. Okay, let me find 644. Here we go. (644), yeah. A charge of minus 30 microcoulombs is distributed uniformly throughout a spherical volume of radius 10 centimeters. Okay, well here, let me draw that. We have a spherical volume, and the radius is 10 centimeters. Do you make a sketch when you do your stuff? You're supposed to. Hope you can read my writing. All right, but it's a spherical thing. It's not just a circle on a piece of paper. It's like a ball, okay? A globe, maybe. All right, and we're going to put a charge of negative 30 microcoulombs. Only this is a non-conductor, and the charge is distributed uniformly throughout. To explain that, I talk about a pot of oatmeal. You go to the kitchen and you mix up and put in some oatmeal and cook it, and then dump in a half a box of raisins. Stir them up good. And so you see you have the raisins. The raisins are scattered all over inside the oatmeal. It's three-dimensional. Only they're not raisins, these are charges, and they're negative charges. So what you're going to wind up with, you're going to get an electric field. It's really in 3 dimensions. It's going to be doing this. But see, it's out here in space going in, and then back behind the board, it's going that way. The electric field is going towards the sphere because it's negatively charged. Okay, let me read this. A charge of negative 30, we did that, microcoulombs, distributed uniformly throughout a spherical volume. They want to know the electric field due to this charge at a distance of 2 centimeters from the center. Well, you see, 2 centimeters from the center, 2, 4, 6, 8. I don't know, it's kind of in here someplace. They're talking about a little, think of a little sphere that has a radius of 2 centimeters. You know what that would be? That would be 0.02 meters, wouldn't it? 0.02 meters. And they want to know the electric field. Well, you're going to have an electric field there. It's going to be going this way. We're going to use Gauss's law, but see, all these charges here that are outside this little Gaussian surface don't matter. Just forget them. All we care about is the charges inside there. Well, what we need is this thing here. It's called the volume charge density. And what it is, it'll be the negative 30 microcoulombs divided by the volume of your sphere. I don't know if you remember the equation for volume of a sphere, but it goes like this: 4/3 pi r cubed. Well, let me show you that in your book. You guys need to know where that is in your book. In the back, there's a bunch of mathematical stuff back here. Let me see if I can find it. There's all kinds of stuff. Astronomical data, mathematical formulas. Hey, in the back of your book, it says mathematical formulas. All right. Now let's see if we can find volume of, hey, there it is. Volume of a sphere. It's right there. It's Appendix E. It's 4/3 pi r cubed. Volume of a sphere. Okay. Well, let's get it. This has a name. It's called the volume charge density. Volume charge density. And I'm going to get it now. Here goes. And I hope you can get the same thing I get. If not, speak up, because I could be wrong. Now we're doing it for this little piece here. We want to find the, no, we're finding the charge volume charge density for the whole thing. So you got to divide by 0.1 cubed. I wonder if I did that right. Here's what I'm coming up with. I need somebody to double check me on this. Doesn't look right. Maybe I forgot the micro. Let me do it again.
For the 0.1, right?
No, we're finding the volume charge density for the whole thing. See, they said you got 30 microcoulombs on the whole thing. So we're dividing by this R here would be, yeah, that's what you said. You're right. It's 0.1. Yeah, absolutely. Okay, I'm plugging all this in now. I want to make sure this is right. Yeah, that's what I got. How about you? Did you guys get this?
I also got that.
Yay, good. We now have the volume charge density. Now we're going to get the enclosed charge. We're going to get this. See, this is what's in Gauss's law. See, Gauss's law goes like this. We have to get the enclosed charge. And this, what this is the total electric flux. That's what that is. Okay. Well, you know what this is? This is the volume charge density times the volume of our little 0.02 meter radius sphere. See, if you take charge per volume and you multiply by volume, you'll get charge. Okay, here goes. We have 7.162 10 to the minus 3. Now we need the volume of this little sphere. Well, that's 4/3 pi 0.02 meters cubed. Okay, do that. Get the enclosed charge for me. Go ahead.
The R is just supposed to be 0.10, right?
Uh,
For the, still trying to get same number density.
isn't it 0.02? Let me read it again here.
Here, I'm still trying to get the volume charge density, yeah.
We're doing part A, and we need the electric field due to this charge at a distance of 2 centimeters from the center. Yeah, so that's 0.02. Yeah.
No. I'm still looking for the volume charge density. Like putting in
Uh,
the thing.
the,
I'm not getting
the
same
volume charge density should be 7.162. Did I do that wrong?
I'm trying to get your number. I'm just not getting
Oh,
the
okay.
same
Well,
number.
let me do it again. Now, who am I talking to?
Jacob.
Jacob, thank you for speaking up. You could get a big fat thank you point for this if I'm wrong, but if I'm right, you don't
No,
get
I
anything.
think you're right. You checked yourself earlier. I'm
Yeah.
just trying to figure out what's going on. I'm not getting the same number.
Now you have to cube this, Jacob. Did you cube it?
Yes, sir.
Well, that's what I got again. I think that's right, and you're not getting it.
Yes, sir.
Do it again. This is a 10 to the minus 6, Jacob.
Yes.
Okay. And this is a 0.1 cubed. Now, I probably should put a minus sign on this, but I know it's minus. Jacob, throw that calculator away if you're not getting that. How about the rest of you? You guys getting this?
Yeah, that's what I got.
Yeah, I bet it's right. Now, if you want the enclosed charge, you have to take the volume charge density times the volume of whatever you want. We're trying to do it for this little volume here. Because see, in Gauss's law, it doesn't matter about the charges outside. All that's going to matter is the charges inside, the enclosed charges.
All right, I figured it out.
Oh, good. What were you doing wrong?
It switched me back into radian for whatever reason.
Well, there's no radians on this thing.
No, I know I should be in degrees. My calculator was in radians again for whatever reason.
Well, even if it's in radians, this should give you the same answer,
I have
Jacob.
no idea then.
Jacob, I want you to learn how to do this.
I got it. No, I got it now. I don't know.
So
what
you're
was going
happy
on
now. All right. Okay, well, now what are we supposed to do? Just a minute, I got lost. They want to know the electric field. Okay, we'll do it. Here goes. Do you see Gauss's law here? We're trying to find this electric field inside here at a radius of 0.02 meters. You can pull that E out because it's constant. And then you're integrating the area of that little sphere, which is, now be careful, the area is 4 pi times the radius squared. Did you know that? Did you know that the area of a sphere is 4 pi r squared? It's in that Appendix A in the back of your book. And then this is equal to your enclosed charge, which we figured out. Wait a minute, I got lost here. Did we never did that? No, just a minute. You've got to multiply this to get the enclosed charge. I don't think we ever did it. Well, we better do it. Here goes. I'm doing it now. Okay, what I'm getting for the enclosed charge is 2.4 times 10 to the minus 7 coulombs. And you divide by epsilon 0. This is Gauss's law. We've got our E, we've got our A. This is the A, 4 pi r squared. This is the enclosed charge. You take your rho times your volume, divided by epsilon 0. Here we're going to get our electric field now. I want everybody to put this in their calculators and solve for the electric field right here. Go for it. Here goes. See if you can do it. Well, I got an answer. I wonder if it's right. Yeah. Yeah, this answer is right. Let me call on you guys. I'll give you a little more time. If anybody has this electric field,
Christy and I both got a 27,106.497.
Something bad happened.
I have 27106.39.
Something bad happened. Maybe you guys are right. Maybe I'm wrong. Maybe I
didn't
need to
do. We didn't do the rest of the math. You want us to bring over the 4 pi and all of that too?
Yeah, I want you to find this value of E here.
Oh, okay. Hold on. Yeah, we gotta finish.
You might have done part of it. You got to divide by this to get the answer.
Is it more like 53926?
Yeah.
That's what I got, yeah.
Yeah. It's 5.39 times 10 to the 6th. We'll be fancy about it, and we'll call it mega newtons per coulomb. 5.39 mega newtons per coulomb. No, wait a minute. Yeah, that's right. We did that right. That's the answer. Okay, now that was part A. Now let's do.
Shouldn't it be newtons per coulomb meter squared?
Say that again, please.
Is it going to be newtons per coulomb meter squared?
No, it's just this is electric field. Didn't they want electric field?
Oh, so it's the flux that has the meter squared?
Yeah, electric field is in newtons per coulomb. Now the M is just 10 to the 6th. It's a mega. I think that's what they wanted. They find the electric field. You don't have any meters squared in the electric field. It's just newtons per coulomb. We did part A, and I think that's the answer. If you don't believe me, we'll look in the back. This is 644. Go to the back, and let's see what they say. 644. They said, oh, wait a minute. It's an even number. I had to look this up in my answer book, but that's correct. That is correct. Well, let's do part B. What do they want for part B? Well, they wanted it 5 centimeters. Okay, you know where that is? That's right here. We're going to have to take a Gaussian spherically closed surface that's 5 centimeters, in other words, 0.05 meters. And the rho doesn't change any, guys. The number of raisins you have per volume in your oatmeal, that hasn't changed any. That's still this right here. But now the electric field here, we're trying to find the electric field here. And it's going this way because the raisins are negative. We're trying to find this electric field. Now what's different, that rho is the same, but the enclosed charge is going to be different. It's going to be rho, which is the same, but the volume changes. The volume is going to be 4/3 pi times, it won't be 0.02 anymore. It'll be 0.05 cubed. Can you read that? I wrote it in green there. It's 0.05. You have to cube it. And so you'll get a different number here. Let's get the new number there, and then we'll do this. Here goes. I'm getting the new enclosed charge, and it's a bigger sphere, see? We have a different Gaussian enclosed surface. So I'm going to take 7.162 e to the minus third, but I'm going to multiply by 4/3 pi 0.05 cubed. Okay. I got a different answer this time. I'm getting an enclosed charge. This is not right anymore. I'm getting an enclosed charge of 3.75 times 10 to the minus 6. Now here, when you use Gauss's law, the area, this is going to be different too. We're taking a bigger glob of oatmeal here. This is going to be 0.05 meters squared. And so you're going to get a different answer. This isn't going to be the same anymore either.
And why did we switch from 0.02 to 0.05?
Because we're taking a different, we're using Gauss's law, but we're using a different Gaussian surface. See, before we had a Gaussian surface of a little sphere like here, and now we're taking a bigger, it's a spherical closed Gaussian surface, but it has a radius of 0.05. So you have to have this, I don't know if you guys can see that. It's not very dark. You got to have a 0.05 here on the new larger Gaussian surface. And we'll get a different answer. Let me go ahead and get this answer, and we'll see what we got. 3.75 e to the minus 6. I get a different answer now. I'm coming up with, this is part B now. Is that showing up on the board? Yeah, I think so, maybe. Yeah. Part B is going to be equal to, holy cow. Wonder if that's right. I'm getting 13.5 mega newtons per coulomb. Yeah. Yeah, that's right. 13.5 meganewtons per coulomb. It's bigger. I wonder why it's bigger. Well, you got more charges. There's more charges enclosed in that sphere than there was in the little bitty sphere. In fact, I think the electric field right at the center is 0. They explain this in your book. Let me see if I can show you the page. Yeah, here it is. This is on page 258. Now I need a little room to show you this. I just don't have enough room to work here is the problem. But here's the thing. If you plot up your electric field versus the radius of your Gaussian spherical surface, this is on page 258. It's linear till you get to the radius of your big sphere, and then it drops off as an inverse square. You'll see that graph on page 258, but it's linear. See it. This radius here is 0.10. What we just did was at a radius of 0.05, I believe, wasn't it? 5 centimeters. And what you should get, if it's linear, the value of the electric field should be exactly 1/2 what it would be right here on the surface. Let's do that together. Here on the surface of this sphere, we could just use Coulomb's law. Yeah, a version of Coulomb's law. K times the total charge, which is 30 microcoulombs, divided by your 0.10 meters squared. That's just Coulomb's law at the outside of your big glob of oatmeal. Do that, and you should get exactly twice this. You should get 27. This should be 27. See this value right here? That should be 27 meganewtons per coulomb. If halfway is 13.5 meganewtons per coulomb, then twice that, it should double. I want everybody to put this in their calculator. You know what K is. Put 30 microcoulombs, divide it by that, and see if you don't get 27. Go for it.
Got real close.
I got close. We rounded off a little bit. We rounded off here too.
Yeah.
But mine says 26.97 on my calculator. meganewtons per coulomb. I think that's actually the answer to probably part C. If you read this problem, what are we doing, 44? No, part C, that's not part C. Part C, they want you to come out here in outer space someplace. They want you to come out here. See, it drops off like an inverse square, like Coulomb's law does, once you're outside. But inside, it's linear. Well, let's do part C, and then we'll quit, and our time will be up. But I think everything I've shown you here is correct. I just need a little room to do part C. They want to go 20 centimeters from the center. All right. Now rho hasn't changed any. That's the density of your, that's what they call that, the volume charge density. It hasn't changed any. But we're coming out here at a radius of 20. So the total enclosed charge is still 30 microcoulombs. We haven't changed that any. So you don't even need Gauss's law. All you need is Coulomb's law. Let me make some room here for Coulomb's law, and we'll do it. Here goes. Here's a little room right here. This is part C. We're just going to use Coulomb's law. Once you get outside here, you don't need Gauss's law. That'll do it. You know, K, Q is given, it's 30, and it's negative, so we know we're pointing in because it's negative. Microcoulombs, and they want to come out here at 20 centimeters, I think. Isn't that what they said? We're doing problem 644 if you just woke up. Okay, do that. We'll get our answer. And I'll tell you what the book answer is. The book says it's 6.74 meganewtons per coulomb. That's what the book says. You do it. See if you get that. Well, I'll tell you what I get. I get 6.7425 meganewtons per coulomb. This is the answer book gets this. And what I get is this. I think we did good on that. And we used Gauss's law. And I want you to read chapter 7 because that's what we're going to be doing next time. I was going to talk about it a little bit tonight, but we don't have any time. We've used all our time up. But here's your chance now. We're going to sign off. The time to sign off has come, but you can say something or ask a question. We still have a minute and a half left. I'm listening.
You said the test would be over which chapters again?
5, 6, and 7. It's on the schedule, and it's on Blackboard. It's kind of crazy. We have to learn a lot every time because we meet for 3 hours.
Are you going to hand out a study guide or anything like that?
No. You're going to have to listen. You might go over the YouTube video. That wouldn't hurt you any. That wouldn't hurt at all. But you guys pay attention to this. You do pretty good on this stuff. But thanks for asking anyway. Anybody else? Okay, well, we're gonna sign off. I'll see you Thursday at 5:30. You can ask me stuff then too. Okay, that'd be good. We'll have our lab on Thursday night, 5:30. See you then. Bye-bye, everyone.
Later.
Right.